Hi everyone, welcome back. In this section we're going to introduce triple integrals. Now I'm going to do it through a problem that is really not a triple integral problem, it's a double integral problem, so it's one we're familiar with, but we'll see how we can look at it as a triple integral, and that'll be sort of our motivating example into triple integrals. So we've got that we want to find the volume of a solid bounded by a plane and the three coordinate planes. So this object here is a plane. And we've got our three coordinate planes that we also want it bounded by, so let's have a little sketch of this region. So we've got our coordinate axes x, y, and z. The plane we're interested in has equation 2x plus 3y plus z equals 6. And so I'm just going to pick off 3 points, namely the 3 intersection points with the coordinate axes. So when does it intersect the x-axis? That's when y and z are both 0, so that's when x is equal to 3. When does it intersect the y-axis? That's when x and z are both 0, so y is equal to 2. And the intersection of the z-axis happens at z equals 6. So once we've got those 3 points sketched, then we can go ahead and sketch in the portion of our plane that lives in the first octant. So there's our plane. It's cutting off some region in the first octant, and that's what we want to find the volume of. It's a tetrahedron, so it's got 4 sides, 4 triangular sides. How are we going to find the volume? Well, the volume we get by integrating the function. Our function in this case is given by the plane, so we can look at it as z is equal to 6 minus 2x minus 3y. So there's our function we're integrating. And the region we're integrating over is going to be this region in the xy plane. You can get a sketch of that just to have a visual for the region we're integrating over. So we're out here at 3, at 2, and so there's our region we're integrating over. And the equation of this line, well, it's where the plane intersects the xy plane. So this is going to be when z is equal to 0, which means 2x plus 3y equals 6. Or we could write it as y is equal to 2 minus 2/3 x. That's the region we're going to be integrating over. We want to integrate our function over this region. I'm going to look at it as a y first integral, so we'll, given an x value, we'll look at a line segment, and then we'll let that line segment sweep over the region. So our volume becomes the integral with respect to y first, so that is as y goes from 0 up to 2 minus 2/3 x, and then we are integrating x next. X goes from 0 to 3. The function we are integrating is 6 minus 2x minus 3y, and so that's dy dx. And so there's the integral that's going to represent the volume, and we can go ahead and we can compute that. I'm not going to fill in the details of the computation here. I want to focus more on the integral setup, but we could go ahead and compute this integral, and we'll get a value of 6 that comes out of it. So we've got the volume is 6. Now there's a couple of things I want to note here. One is we do actually have a formula for the volume of a tetrahedron, just like we have a formula for the area of a triangle, base 1/2 base times height. We also have one for a tetrahedron, so let's just make a note of that fact up here. For a tetrahedron, I'll draw our coordinate axes in just to get a feel for it. So maybe we'll do a slight rotation of our coordinate axes. So there's our x, y, and z axes. And our tetrahedron is going to look like this. So it's going to be all of the stuff in the first octant. And we'll say it reaches down here to a point along the x-axis at a point A, point B on the y-axis, and a point C on the x-axis. So in other words, our tetrahedron has these lengths, A, B, and height C. So it turns out in this case the volume is given by 1/6 of A times B times C. So that's a fact that we have about tetrahedron, sort of the analog to the area of a triangle formula. Now it's a volume of a tetrahedron formula. The main idea though is that we can prove this fact. It's nothing that we have to memorize or recall from previous courses. We can now prove a result such as this because given the values of A, B, and C, we can write down what the equation of the plane is, and then we can construct an integral much like we've done here. In our case, A, B, and C are 3, 2, and 6, so the volume should be 1/6, 3 times 2 times 6, or 1/6 of 36, or 6, and that's what we got for our calculation. So we could verify this fact, or actually create this fact from a double integral. So that's one aspect I wanted to bring this example up for, is that we can use this to verify results about tetrahedron. The other reason I wanted to do this example is because we could look at this as a triple integral. So it's not going to help us compute it, but it will help us think about where triple integrals can come from. So I'm going to write this first integral down, still 0 to 3. I'll write the second integral down, still 0 to 2 minus 2/3 x. And then I'm going to write down this third integral. This third integral, maybe I'll change the color of this third integral, because this third integral is really just coming from that integrand. So if I think about that integrand, currently I have a dy dx as my integration variables for those outer two integrals. But then that integrand inside, 6 minus 2x minus 3y, I could look at that as the integral from 0 to that same thing, 6 minus 2x minus 3y of, and that's the integral of 1 dz. And so that integral I just wrote down, that innermost integral, and I'll put it in parentheses, parenthesis there and a parenthesis there, that innermost integral just evaluates out to be this integrand. But I've written it now as a triple integral just to introduce the idea that we could use these triple integrals to represent the volumes of regions. In this case, the triple integral is the triple integral of the constant function 1. And what's really happening is in that integral, I can now think about this idea of integrating over region or sweeping out the region. So my first integral, the z integral, goes from 0 up to the point on the plane. So I pick an arbitrary point in our xy inputs or xy plane in the domain, and then I draw a vertical line segment. What I want to do is I want to integrate over this vertical line segment first. So that's going to sweep out a vertical line segment in my region. That's that innermost integral, that integral of 1 dz from 0 up to 6 minus 2x minus 3y. And then I'm going to let that line segment sweep out all the points above that footprint, that orange footprint, or that region in the xy plane. So as that line segment sweeps out the rest of the region, that's this part of the integral. So first we integrate with respect to z, and then we let that line segment sweep out everything in the domain, that xy region, that two-dimensional region in the xy plane. And so what this is doing is it's integrating over all points in that solid. And when we integrate over all points in the solid, what we get is the volume. So that's a way to interpret that volume, that double integral, as a triple integral. Okay, so that's just, again, just a bit of a motivation as to where these triple integrals can come from. We'll also see in the next few examples other interpretations of where they would come up. So this idea of introducing a triple integral by sweeping over all the points in the region, now we just have to figure out how to set these things up for a given example. So in this context, we're going to suppose that the region, this three-dimensional region E, has piecewise smooth boundary and is z-simple. So that just means that in the vertical direction, if I draw a vertical line, then it's going to intersect at some upper surface given by a function of x and y. That's what we call h sub t, or the top function. And we'll call this the top. And there's also the z values have to be bigger than whatever the function value is for hb of xy. So there's our bottom. The way I like to think about this is I'm going in the z first direction, so I'm integrating with respect to z first. I imagine these vertical line segments, and then I watch what happens as they sweep out the region. Well, wherever they have their highest value, that's going to be the top surface for the region. Wherever they get the lowest value, that's the bottom for the region. So again, that's on the bottom, this is on the top. And if there happens to be a spot where when I drag that line segment around, I get that all the points on that line segment live on one of the boundary surfaces, then the boundary surface that it lives on is called a side. So we've got this idea now. We've got a three-dimensional solid, and there's surfaces that bound it. Now we've got this idea of what are the top, what are the bottom, and what are the side surfaces. And they depend on our perspective. I'm thinking of a z-first integral, so vertical direction is the direction that I'm interested in. That's sort of my direction of orientation, so I'm interested in vertical direction, so my top is the highest point and my bottom is the lowest point. And once we've got that figured out, then our triple integral over this region E of a function is we first integrate with respect to z, our function, as the z values go from the function that defines the bottom part of the surface to the top part of the bounding surface. And then we integrate over the footprint, what we call the footprint or the shadow. We integrate over that afterwards, and that's just our double integral. Now, it's not always going to be the case that we integrate first in the vertical direction. It all depends on the solid itself. So that's what we're going to talk about now. We really have the choice of integrating with respect to x first, y first, or z first. So these are the questions we want to ask ourselves when we're setting up a triple integral. So the first question I want to ask is, what is the footprint or the shadow or the projection once I've picked a variable for my variable of integration that I'm going to first integrate with respect to? What is the projection of the solid into the other two variables, the plane defined by the other two variables? So the way I like to think about this is I like to think about just carrying a light bulb around and then looking at what the object projects to. What kind of shadow or footprint does it have in the other plane? So if I hold it over here in the x2 direction, then what it's going to do is it's going to cast a shadow. This object is going to cast a shadow. So that I take the sort of widest part, and it's going to create this shadow in the plane given by x1 and x3. So this would be the footprint if I was to do a x2 first integral. If I do an x first 2 integral, I'm interested in the x2 direction, integrating this way first, and then I'd have to figure out what are the values in x1 and x3 plane that I have to sweep over. That's this footprint. And so I just check to see if those are things that I can work with. Are those equations that are easy to deal with? What if we take our light bulb and we maybe put it up here, so in that x3 direction? Then what is our footprint going to be? Well, it's going to shine down on top, and so our footprint is going to be something that looks like this. That's sort of the shadow that's cast. And our integral would be, first we would integrate in the vertical direction, and then we would let those red line segments sweep out the entire blue region for our 2D integral. And lastly, if I decide that x1 is the direction I'm going to integrate with respect to first, I'm imagining my light bulb over here, and then the shadow that's cast is given by that domain D in the picture. That's our footprint. So this is what we call our footprint or shadow. And when we integrate, we are integrating over the x1 direction first, so that's along a line segment like this, and then we are letting that line segment sweep over all points above our footprint, so then it reduces to a 2D integral. So the main takeaway with these questions that we want to ask are really about these directions. So once I picked a direction such as this, then I want to figure out what is the anatomy of the region. So I've got a x1 region first. I've identified the footprint, so that means I've answered question 1a. There's the footprint or shadow. What are the sides? Does it have a top and a bottom? These are all questions about the 3D geometry. Now, sides, top and bottom, can I pick these things off? And they're all going to be picked off by imagining this little red line segment sort of sweeping over the region. So the first thing I notice is that a red line segment, it's got a smallest x1 value and a largest x1 value. The smallest x1 values are the things that correspond to the bottom. So maybe I'll take a step back. I've got this object now, this sort of reddish orange colored object in the picture, that big 3D solid, and it's got bounding surfaces on it, so the boundary surface. I can split those boundary surfaces up into a bunch of components. So there's a couple of flat components and this sort of rounded side component. So I'll put side in quotes, this sort of rounded component as well. I want to classify them in terms of the x1 first integral. I want to classify them as either tops or bottoms or sides. And in this case, I'm classifying that one as a bottom. This one up here, I'm going to classify as a top, because for this red line segment that goes in the x1 direction, those are the highest values on that red line segment. And then I imagine dragging this red line segment around. I still have this other surface I haven't really talked about yet, but that other surface, I should say, the points on that other surface, when I look at a red line segment such as this one and this one, those are lying entirely within that surface. So that is what I would call a side. It's a side relative to this, or relative or with this x1 first perspective. So those are the sides. And that's telling me how I can sort of answer question 1b and 1c. I think about the direction I'm going in, I draw a little line segment, and I think about where is it going to hit the highest point on the surface, the lowest point on that surface, and where is it entirely contained in one of those bounding surfaces, and that classifies tops, bottoms, and sides. Once we've got that all taken care of, then we go and work on the 2D geometry part and how to integrate that. And so that's this next question. Question 2 is about the 2D geometry. And the idea is to first deal with the 3D geometry, pick off one of those dimensions, and then drop down, and the resulting 2D geometry is what we deal with next. And so that's this part. These are getting this one set up is questions 1a, b, and c, and then getting this part set up, that is question number 2. Maybe I'll put little pound signs in front of it. Number 1a, b, and c is setting up that inner integral, and then question number 2 is about setting up that outermost integral. Let's have a look at an example. So I admit we've been completely abstract up till this point. It's kind of a challenge to get a hold of what it is we're actually doing. So if we look at a concrete example, a lot of these things should fall into place. So let's evaluate this triple integral of the square root of y squared plus z squared, where E is the region bounded by the paraboloid and the plane. So the first thing to note is that we've got our function that we're trying to integrate. Let's call it f of x, y, z. And that we don't have to do anything with right now, because that's just the thing we're going to integrate in the end. Right now we're interested in setting up this triple integral. How are we going to integrate over all the points in this three-dimensional region? So we'll start by getting a sketch of this region. So got our coordinate axes x, y, z, and then this parabola or paraboloid. It's going to be a parabola in the xy plane. Maybe I'll dot this because it's going to be behind the surface, so something like this. So there's our, trying to draw a little bit of perspective here. There's our parabola in our XY plane, and I'm sort of just connecting these across with a point to say they're at the same X value. And then we've also got a parabola in the XZ plane, so maybe something like this. So there we go. And then we can connect up all these points here. And so there's our paraboloid. How far have we gone? Well, we've gone to x equals 4. So we're out here at the point x equals 4. So there's the solid we want to integrate over. Now this solid is going to be made up of our paraboloid, which I'll just sketch in green here. So it's our paraboloid. And then we've got this end cap at x equals 4. So there's our end cap at x equals 4. And we want to integrate over that entire region. So I have to decide what variable do I want to integrate with respect to first, and then answer those 4 questions regarding it. So let's look at an x first integral. And we'll answer those 4 questions. 1a, what is our footprint? 1b, what are our sides? 1c, what is our bottom and top? And then we have question 2 about the 2D geometry. So we've got our picture there, but let's just go to a visualization. And so there is our paraboloid with that end cap. And what I'm interested in is trying to figure out which direction should I integrate with respect to first. So if I come along in the x direction first, it means that I'm ultimately interested in, for the 2D geometry, this footprint. The projection of this solid onto the YZ plane. And that's going to be a circle. That's something I can deal with. So that's what we're going to do. We're going to do the x first direction, so we are going to integrate along the x direction, and then the 2D geometry is to integrate that shadow or that circle. Now when I go along the x first direction, I have to think about, as I come along the x direction, what's the bottom, what's the top of this surface, are there any sides? And this is all dependent on the x direction. So I imagine coming along the x direction, where do I start in the solid, where do I end in the solid? And if I travel along a straight line, is there any sides of the solid, any, I should say, bounding surfaces, which the line segment lies entirely within? So we imagine taking a line segment in the x direction. What point does it start on the surface, travels through the region, and then just before it exits the region or exits the solid, it passes through another surface. And those are the surfaces where it starts. Smallest x value, largest x value. So smallest x value where it starts, that's the bottom. Largest x value that it passes through before it leaves the solid, that's going to give rise to the top. And if it happens that the entire line segment lives on one of the boundary surfaces, then that boundary surface would be a side. In this case, we don't have any. We don't have any sides. We basically have 2 boundary surfaces. We have the paraboloid and that end cap. And the paraboloid forms the bottom, and the end cap forms the top. So we've got, for sides, we've got none. For bottom and top, the way we describe those is by just indicating the inequalities on x. So x has to be bigger than the points on the paraboloid, y squared plus z squared, and smaller than the points on the end cap, which are corresponding to x equals 4. What about our footprint? You notice I'm answering these questions out of order. Really, these first 3 questions, they are called 1A, B, and C because they're all grouped under the heading of question number 1, and you could really answer them in any order. The footprint, since we're looking in the x direction as our x first integral, then the footprint is just the projection of this solid onto the YZ plane. And so the projection of that solid onto the YZ plane, that forms a circle. So we'll call this footprint. What is this circle? Well, the circle is really coming from, in some sense, that end cap. So that's why I'll shade it in the same color. But to be precise, it's really this intersection curve. I'll highlight it here. The intersection of the plane and the paraboloid. That's the circle that's being projected into the YZ plane as the boundary curve for this footprint. And then it's being filled in because it's a solid. So how do we get that boundary curve? Well, that boundary curve is the points y and z on the paraboloid, which correspond to an x value of 4. So this is where the plane and the paraboloid intersect. So it's y squared plus z squared equals 4, and that's a circle. So this is a circle of radius 2 in the YZ plane. So we've got our footprint. It's a disk in the YZ plane. I'll just point out that I use the word disk here. Circle is a one-dimensional object. It's a curve. The disk is that boundary circle with all the points inside it. So this would be called a circular disk, so we'll call it D. The disk in the YZ plane, we'll call it D. So we've answered our first 3 questions. The last question we need to answer is about the 2D region. We've already got an idea of what the 2D region is. That's the footprint. Now it's really here where we indicate our integration plan for that 2D region. So that 2D region is the disk D. It's described by y squared plus z squared is bigger than or equal to 0, less than or equal to 4. And so there's our circular disk. We could describe it, it's the y values between -2 and 2. I'll put that in here just to be precise. So we could describe it as a set of all y values between -2 and 2, and the z values that are between negative square root of 4 minus y squared and the square root of 4 minus y squared. So that's just the upper semicircle and the lower semicircle. That's one way we could describe it as well. And if we were to do just the integral over this circular disk, then those would be our limits of integration on y and z. But this is a circular disk. We probably want to go with polar coordinates. We've learned about polar coordinates now, transition or change of coordinate systems, how the integral would change, the double integral would change. It's probably in our best interest to go with polar. We'll just keep that in the back of our heads for the time being. So now let's go ahead and set up our integral. We've got all of our previous setup done as we think we need at this point, but we'll see. Now the integral. So we're going to do the triple integral over the region of our function f of x, y, z dz. Based on the questions that we've answered above, we've got our integration plan, at least the innermost plan. The innermost integration plan, or the first integral, is going to be the integration with respect to x, and that'll go from y squared plus z squared up to 4 of our function f of x, y, z dx. So that's our innermost integral, and then our 2D integral will be the integral over the disk afterwards. Now that's the question. What do we do for that integral over the disk afterwards? Well, I've already indicated that we'd probably want to go polar. So the idea is we would make this change to polar coordinates. So if we go polar, that means y is equal to r cos theta, z is equal to r sine theta. You might say, well, normally you go x is r cos theta, y is r sine theta. Yeah, but we're going polar in the yz plane. So we're looking at the footprint, the bottom diagram on the left. And in that diagram, to go polar, we will say y is r cos theta, z is r sine theta. So then what happens is our region, as described, the circular disk, as described in polar coordinates, is given by r is between 0 and 2, and theta is between 0 and 2 pi. So there's our nice description of our 2D region in polar coordinates. But if we're going to switch to polar, we might as well switch everything to polar. So that means switching this to polar, y squared plus z squared, that is r squared. So that becomes r squared is less than or equal to x is less than or equal to 4. So there's our essentially our limits of integration for x in polar coordinates. One last thing we have to switch to polar is the function itself, our integrand. And switching that to polar, y squared plus z squared is r squared, square rooted is just r. So we've now got everything we need in order to switch to polar coordinates. Let's write out the integral. So maybe I'll indicate here. We are changing or change to polar. So we've got our 2D integral, which we'll deal with, our multiple integral, double integral, over the integral over the 2D region, which we'll deal with in a second. Our innermost integral is the one with respect to x. Now that goes from r squared to 4. Our function is r. Then we've got a dx. And then we've got our dA, that when we change to polar coordinates, we'll indicate that here, the change from dA to polar coordinates, that becomes an r dr d theta. So that's an r dr d theta. And so what I can just notice is I've got now two r's, so an r squared. So I'm just going to take that r, I'm going to put it with the other r as an r squared, and then we've got the dx dr d theta. So that's our change to polar coordinates. Our region D, when we change to polar coordinates, the r goes from 0 to 2, and the theta goes from 0 to 2 pi. So there is our integral change to polar coordinates, and this is now quite straightforward for us to integrate. First integrals with respect to x, r squared is a constant with respect to that, so this first integral is really just integrating a constant, evaluating at the endpoints. Then we integrate a polynomial with respect to r. There's no theta anywhere, so really that integral involving theta, we just get a factor of a 2 pi coming out of it. So this all boils down to give us a result of, I'll put dot 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 here, because you can fill in the details, you can get some practice integrating these. The main point was getting the setup. And so this boils down to 128 pi by 15. So again, it's not the calculation of the integrals in the end that we're really focused on here, because that has just reduced, we've just reduced this problem down to 3 calculus 2 integrals essentially. So the main emphasis I want to point out in this section is about the setup of the triple integrals. That's where our effort is going to be placed, in the setup. And you can see that there's a lot to do with a setup in a problem like this. Alright, so that's it for this example. I've split off the remaining examples each into their own videos so that you can watch them at your discretion. Alright, so we'll see you in the next video.